Welcome everyone. So today's webinar topic is about anti-cavitation valve design using CFD, and we'll see how our advanced technologies or CFD simulation application will help you to accelerate your design process and reduce the time to market your product. Okay, so a little introduction about myself. So I'll be your presenter for this webinar. So myself, Praveen, I am currently working as a product marketing manager in Simulation Hub. I'm basically a mechanical engineer with a PG diploma in CFD, and I have over 15 plus years of experience in applying CFD in various fields, including valves and HVAC. So valves is one of my expertise. It's valve simulation specifically. And recently, I furthered my expertise in PG cert. Like I completed my PG certifications in product management from IIM Indore. Now, in Simulation Hub, we are developing cutting-edge CFD technologies to transform uh, industries. In the context of today's webinar, we are developing CFD technologies to transform valve industries. Okay, so without further ado, we'll start into the topic. So this is the agenda of today's webinar. So first we'll start with understanding what is cavitation and what is cavitation in valves particularly, and how do we estimate or evaluate the intensity of cavitation? How do you measure cavitation in valves? And then later we will move on to, what are the different methods to calculate the cavitation intensity or cavitation index. Then we'll see how to use the advanced applications, safety applications, to calculate the same thing, same cavitation index. So we'll have a app demo, and then we'll end with a Q&A sessions to answer your questions. So meanwhile, while I'm presenting, if you have any questions, you can post it on the chat, and my questions will be collected, and that will be answered towards the end of the session. Okay, so first we'll start with what is cavitation. So cavitation is a phenomena like that is, whenever in a flow stream, whenever there is a liquid whose liquid's static pressure drops below the vapor pressure of the liquid, then a vapor bubble forms, and that bubble, when the fluid, like the liquid, tries to recover the pressure, then it implodes, and that phenomenon is completely called, cavitation. So it has some impacts on the nearby surfaces. It erodes and it causes some damages that we will see in detail in further slides. So this is just cavitation for you. And cavitation in valves, control valves particularly. So first, we need to understand what is vena contracta. Vena contracta is the minimum area of flow stream, where the velocity will be highest in the complete valve domain, the valve fluid domain, and the pressure will be the highest in that region. So whenever the fluid velocity is the highest and the pressure goes the lowest. So cavitation occurs when this pressure at the vena contracta area goes below the vapor pressure of the liquid. So then the bubble forms, and whenever downstream the flow, whenever the pressure recovers and goes above the vapor pressure, then the bubble collapses. So this is cavitation, and there is another term called flashing. This happens when the outlet pressure, there is no recovery happened once the bubble formed, and it just developed, and it didn't get the scope to recover, and the outlet pressure remained lower than the vapor pressure. So this condition is flashing. So where even choke, it is somewhat related to the choke flow also. So there is no further increase. Even if you increase the pressure drop, there won't be any further increase in the flow rate. So that condition is choked flow. So next one is impact of cavitation. So we saw cavitation in valves, and now we are discussing about what is its impact, why we need to combat cavitation, why we are discussing about cavitation, because it causes issues to the valves at different levels. One, it starts with the material damage. So whenever the collapsing bubble, it creates a local shockwave kind of effect and hits the nearest surface, and it erodes the material. So it starts from there. It damages your valve trim and valve body, and then it creates high noise. The cavitation phenomena itself, it creates high noise and excess vibration to the structure, and it also deterioration of flow effectiveness. So when there is vapor bubbles formed, that in turn affects the flow. So you can see the damages it can cause to the trim. So, what are the different methods to combat cavitation? So, there are four major categories. I'll put it that way. So, one is to avoid cavitation, which is to play with the process or operating conditions. So, when you have your head or pressure head operating pressure high, you elevate your operating pressure such that you're far from the your minimum pressure or vena contracta pressure is far from the vapor pressure. So it's very high. Okay. The second one is robustness of the material. So to you increase the strengthening or harden the material of trim, so that can withstand the the effect of cavitation for a longer period. So the next one is isolate cavitation. So this the second the isolate and the eliminate, these two parts are kind of playing with the design or using the valve design to first one, isolate. It attempts to direct the cavitation in the center or away from the valve surfaces or trim surfaces, so that the cavitation happens in the middle of the flow stream and not near the surface. So this is isolating. The other one is eliminating cavitation. So this is very interesting. So you need to make the valve design such that there is no sudden change or sudden drop in the pressure. So for example, the orange one in the graph, so that is the sudden pressure. If you see the blue and the orange, both are having a same inlet pressure and outlet pressure, but with the orange one with the a regular valve or not so well designed valve, so cavitation happens due to a sudden drop in pressure at the vena contracta, and when you stage it, you reduce or step by step waterfall kind of pressure drop, so that avoids making your vena contracta pressure go below the vapor pressure. So that's how you reduce or you eliminate the chance of cavitation. So there are different ways to do it. So this is the conventional cage. It has some holes in it, and then you have single stage and multiple holes, double stage. So lot of designs are available in the market. So lot of ways to achieve this, to eliminate the cavitation with the help of stage pressure drop. So far we have seen what is cavitation, how it impacts the valve performance, how it damages the valve trim, and how to eliminate or combat cavitation. Now, how do you measure cavitation, intensity of the cavitation or effect of the cavitation, right? So there are two major parameters. One is the cavitation index. The other one is the liquid pressure recovery factor. So cavitation index, it's a fraction of the maximum pressure difference, pressure drop within the domain, and compared to the ratio of that to the overall pressure drop from inlet to outlet. So you have the upstream pressure minus vapor pressure and upstream pressure minus downstream pressure, the ratio of that. So similarly, FL, to explain FL, I'll have to explain this graph. So let's say if you plot a flow rate versus square root of pressure drop, then as you increase the pressure drop, your flow rate should keep on increase, right? That's the ideal expectation. When the flow rate, when the pressure drop increases, the flow rate increases. CV remains constant. So that's the ideal curve. So the line should extend like this, okay? But what happens is beyond a point where the cavitation starts, that is the incipient of cavitation point. Beyond that, and then it starts reducing, the bubble formation and bubble collapse, all those things happen, and beyond certain point there is no further increase in flow rate. Even if you increase the pressure drop any further, there is not going to be any increase in flow rate. So that condition is called choked flow. So the pressure drop where it starts, the choked flow starts, that is required to calculate the FL. Okay, or you can have a Qmax, and Qmax can be used to calculate the FL as well. So in both the cases, uh, how do you, let's say you calculate the FL and cavitation index, but how do you know whether it is, what is good or bad? So you can say something like, higher the number, higher the cavitation index or higher the FL, the lower the chances or intensity of cavitation will be. So when you have higher FL, the recovery factor, the recovery is not so good. So that is better for cavitation. So for example, if you compare different valve types, so compared to globe valve, which will have a high FL number, and ball valve will have a low FL number, and ball valve recovery is very good, but that's going to create problem. That is the cavitation part. So compared to globe valve, ball valve will have it more. Ball valve and butterfly valves are more susceptible like to cavitation. So that's how it is. Higher the number, less lately, or it can delay or lower the intensity of the cavitation. So how do you measure cavitation in flow loop tests? So they fit the accelerometer they calculate the cavitation with the help of noise and vibration. So they fit the accelerometer and plot the cavitation index. So you can see the cavitation index. This is the graph versus the accelerometer output. So you can see different turns of this graph. So this region indicates it's normal. The cavitation index is above 2. It's okay. It's normal operating conditions. And this is the point. The point A is the incipient cavitation index where small bubble formation has started. And it goes to point B where a constant steady popping or cracking of bubbles you can hear, and it's clearly audible. And that region is called constant cavitation index. It has started. And the point C is choking cavitation, which we saw earlier. The flow rate it will not go, increase beyond this point. So that is choking cavitation. So generally what people do is you take the incipient cavitation index. So that will help you to identify, okay, whether for your operating conditions, whether the valve will be cavitating or not. Okay. So that can be identified using incipient cavitation index. But how does this whole process works? It starts with, let's say you have a design target or design requirement. You're developing a new product for a customer or for industry, and you have certain design requirements. You have certain target CV, torque, or if it is rotary valve, and cavitation index or some cavitation performance is a target, FL and those things. So you have, based on those requirements, you design your valve, you create a prototype, send it to the flow loop test facility, and get the test results and cross check whether it matches or not. If not, then you need to do some design changes and follow the loop again. The same thing goes again. But there is a catch here. So you need to, let's say you couldn't meet the expected design target values, but on what basis you're going to change the design, where you're going to change the design, right? So you do not have uh, much of flow insights. You, from the lab results, you will get the final values, but you do not know what to be done, where the changes needs to be done, where the actual low pressure regions are there, where it is cavitating exactly, right? So that is not very clear. Okay. So that visualizing the flow separations, what is causing the consuming the energy, and what is causing the cavitation, where is the region, low pressure region. So those things are not clearly uh, visible from the flow loop testing. So that is one downside of it. And then each design change, it will cost, and it includes cost and time factors, and a lot of carbon credits. Yeah, carbon credits is important in the current context of sustainable green. Uh, so the third one is the resource limitation itself. The lab might be limited to test the diameter of large size valves. So on the contrary, if you take the path of CFD simulation, you will be able to see all those flow insights. So you'll get pressure values at any location inside the valve, the complete quantitative data as well, and then the region of flow separation, what is the lowest pressure location, and everything. So this will help you to make the design changes and go towards the optimum valve design for optimum efficiency. So still there are some challenges in the conventional CFD. So to use this CFD simulation, you need to be an expert in that field. So it involves a lot of manual intense CAD cleanup, fluid volume extraction, mesh generation, and you have to deal with solver divergence. It's a nightmare for any CFD engineer. So you have to be a CFD expert, and it demands high performance computing machine setup in house, and the software licensing costs, like number of users, number of engineers or designers who can use the software at the same time, and renewal of the software. Though these are the challenges in conventional CFD software. So we at Simulation Hub, we understand with our vision of transforming human life or transforming the industry by taking this wonderful technology to the hands of every people, so designers. So with this vision, we created the Simulation Hub platform. So it is an AI powered autonomous simulation platform where we have built applications, CFD applications for different verticals, different industries. So in today's context, we'll see one of such app built on this Simulation Hub platform. So it's completely cloud-based CFD simulation app developed tailor-made for designers. So they should not be worried or concerned about knowing CFD or learning CFD. So they themselves should be able to evaluate their design performance using CFD simulation. So this is the current autonomous valve CFD application that is based on the Simulation Hub platform. So it is, I'll put it this way, it is a virtual flow loop test plus additional app. So whatever you can do with the flow loop test, that you can do, and additionally, much more flow insights and everything you can get from the application. So it is powered by Autodesk Platform Services to view the viewer, the complete post processing, the CAD model, everything that is based on the Autodesk Platform Services, AWS, Amazon Web Services we use for cloud simulations, and then OpenFOAM is the backend solver, and all this built on Simulation Hub platform, Simulation Hub web services. So these are the standards we refer for formulating or calculating the flow performance, and M49 is particularly for the cavitation and torque. So you can see, yeah. So what this app, how it works actually, what it does. So it's very simple. So the inputs required to use or run the simulation through this application is you have a CAD model with you, valve CAD model, and you specify certain details like what is the flow direction. Is it a flow to close or flow to open valve, right? And some operating conditions, the minimum opening to maximum opening. So what is the operating conditions for which you want to evaluate the performance? So you submit that to the application. So it provides you multiple outputs. So it starts from, it could be velocity contours, which will give you the flow separation where the velocity is high, and flow lines will tell you where the recirculation zones are. So how the flow streams, go into the trim holes and everything, so that you can visually get that idea. And multi-stage pressure drop you can get. So, and surface pressure will tell you where the minimum pressure location is in the on the valve trim. So along with that, you get the performance data, which is the main output. So it includes cavitation index, CV, CDT, head loss coefficient, and much more. So all these things combined in an automated, auto-generated CFD report that you can readily hand over to your client. So these are the, in a nutshell, this is AVC for you. So you have input and outputs. So the new features which we have brought recently is to support anti-cavitation trim design in specific. So we have added additional advanced mesh refinement features to capture those, very complex flow path and everything. And also, we included the incipient cavitation index performance data table. So we can make use of that, and based on the cavitation index, you can calculate whether the operating conditions are going to cavitate or not, so that you can evaluate. So using these features, so we are able to simulate very complex structures created using additive manufacturing. So additive manufacturing is kind of, in a way, enabling valve manufacturers or pushing them to go beyond their imagination and create very complex path, and to test their effectiveness and performance in specific to cavitation and noise reduction, and vibration and leakage. So for example, for every leading manufacturer like Bray, Emerson, Samsung, IMA Critical, so everybody is using additive manufacturing to create such complex flow path trims, and our simulation platform, our application supports such high complex trim designs as well. So now we'll watch the demo of this application. So as I said, this is a web application, so you don't need to install on your machine. You can go into your web browser and log in. And this is the dashboard of the application. So here you can create the simulation, can provide a short description and name, and you can create a simulation on your own. So now the first step is to upload the geometry. So you can upload your CAD model in STEP, IGS, or any format, Parasolid, or any format you have. So that is supported. So here you have to enter a few valve details. So what is the valve function? Is it a control valve or on-off valve? Is it a linear or rotary motion valve? And what is the valve type? Is like there are number of types we support. So butterfly valve, ball valve, and globe valve. So all this, you can select the valve type and the trim type as well. So you can select the size of the valve and provide certain inputs like what is the pipe schedule, roughness, valve roughness, and pipe roughness, material. So once this is done, then you're all set to start with the first step, which is specifying which are the moving parts of the valve. So here you're selecting the moving parts and the axis of motion. So, and what are the valve flow conditions for which you want to simulate. So once that is done, you can preview the motion to cross check, whether it is in the right direction. So this is the advanced mesh refinement feature. Usually the autonomous mesh generation algorithm takes care of things, but in addition to that, so if you are a CFD expert for advanced users, we have opened this option as well. So you can now, based on the hole size, you can apply more further refinement as per requirement. So you can select the body part on which you want to apply a certain mesh size, and you can apply this. So next stage is specifying the flow direction, which is the inlet, and what is the outlet pipe. So this specifies the flow direction. So here is a flow to open case. That's it. So we are set to run the simulation. Now the simulation is submitted. It is running on the cloud. So it has started all the processes: fluid volume, mesh, solve, post. So one by one, it will submit. Once it's completed, so you will get an email notification, and you can come back and continue from where you left. So you can, in the result stage, we have provided a lot of post processing tools to get flow insights about the design. So we'll start with the flow lines animation. So that this will help you to identify, where are the flow recirculation happening? Are there any stagnant zones? So those things can be viewed in detail using the flow line tool. So you can view the same for different opening conditions. You can color it by velocity or pressure, and you can increase the speed and those things. So moving on to the next tool, which is surface pressure. So this will help you to identify what is the where there is a high pressure region and where is the low pressure region on the surface of valves. So, and next one is contour plots. This will again help you to see how the velocity or pressure varies throughout my domain from inlet to outlet at different region of my flow. Okay. Okay, next one is the performance data. So this comprises everything: the CV, KV, head loss coefficient, cavitation index. So all those values, including the gross and net. So everything will be present in the performance data. You can export it, and you can see the graph as well. You can save this graph and export in CSV format. So now finally, you can go and have a look at the auto-generated report, CFD report. So this is auto-generated. You don't have to, work on this. So directly you can submit it or hand over to the client. So you can have a look. This is summary of all the flow insights which are available on the result stage. So it includes performance data as well, and then the graphs. Includes the CFD simulation results for every opening conditions. And at last, the incipient cavitation performance table is also included. So you can have a look at what is the minimum pressure and what is the incipient cavitation index. Okay. So that's about the application. Now I'll explain, or I'll tell you an interesting perspective. So how this application is going to reduce the time to market your product, right? So from design to simulation. To understand that, we need to little bit understand how it operates in the backend. Okay. So when you submit an input valve design to the application, AVC application, so it starts a dedicated uh, Amazon EC2 instance, 36 core machine, and then all these processes, CFD processes, cat cleanup, meshing, solve, everything is done autonomously, has started autonomously on the cloud. Okay. So once it is done, then the simulation results and other performance data are available on your web browser for your use. So now it is just for one opening, let's say. Okay? Same thing happens for every percentage of opening. So when you submit the valve design for the whole range of openings, all openings is going to it's going to start a dedicated machine for every opening, and all the processes will run parallelly. And at the end of the simulations, you will get the complete curve, not just one opening results, but complete curve along with the results and the report generated. So it's not just this. So let's say you have multiple valve trim designs in your mind. You want to test every valve trim design parallelly, and you want to have the results and compare it. So you can do that. There is no limitation on the number of instances or number of simulations you can start from one account. Right. So if you have three design options in your mind. You can submit all these three design options at the same time, and all three design options for all of their opening range, the full opening range, the simulation CFD process will happen autonomously on the cloud, and finally you will get three, CV curves or cavitation index and everything to compare with. And adding to that, like you can submit different product lines and product designs of your company at the same time from different geographical location. There is no limitation on that as well. So this explains, how fast it's going to, how it has accelerated your time to market, like the design and simulation part. I'll present you one case study, which is very interesting case study. So uh, this is a comparison of the conventional CFD approach, where you depend on the simulation expert. All the process is manual, the cat cleanup, fluid volume extraction, meshing, and solver, everything is manual, and limited resources, and then the results take time. So compared to simulation of CFD, everything is autonomous, and it's on cloud computing platform, and results are available in hours. So this is the case study I was talking about. So before this product is developed, we ourselves were providing consultancy services with help of conventional softwares. Uh, for that, one of our customer, where we took around 10 days. The same case now, when we run with simulation of AVC application, it takes 1 hour. So this is the beauty of this. So we have reduced the simulation time from days to hours. So now I'll present you some customer success stories. So these are our current customers who are using and exploring our app, evaluating our application, and using in their new product developments and creating data for legacy designs and stuff. So Bray is one of our prime customers. We have engaged with Bray for last 5 years. So these are kind words from Bray CMO and CTO, Brindesh Dhruva. And then we solved their challenge of spending more time and money on the experimental methods for each and every design iteration. So with the help of this, their usage of CFD increased year by year. And now we have also, in the relevant of current topic, we have also helped to develop and validate their design on noise shield, one of their latest or innovative design for segmented ball valves. So we have also helped, we are also part of digital transformation of Dell valve. So it started from having the drawings to CAD model, to now they are simulating more than 300 valves for every quarter of year. So that's a huge transformation, I would say. So they are doing good. We have become trusted partner for them for large valve flow verifications and design optimizations, I'd say. And Magwen is newly added in our profile. So they are our esteemed customer. They used Simulation Hub to test their large plunger valve product. So these are some kind words from GM Engineering. They have used our product for number of valve types. To be specific, like to highlight, I wanted to highlight a large valve size really to 2500 DN butterfly double offset butterfly valve. So some more challenging projects we took. So to reconfigure valve trim of angle globe valve, and we have helped them to achieve the required design in a shorter period of time. So I'll present some validation study related to cavitation. So this is it's a sharp edge orifice. It's a test data taken from this paper. And this is the cavitation accelerometer test data. You can see where is the incipient cavitation and where is the constant and choking cavitation. So these on the right side is the CFD results. So where the choking happens, and we plotted the complete curve. And the takeaway here is we are able to match the test data of about 93% for incipient cavitation and more for FL and CV. So in the context of today's topic, we are able to uh, be in that zone of more than 90% accurate, 95% accurate range. So other validation studies, we have done a lot of validation studies, comparison with Utah Water Research Laboratory data and FCRI data. So all these cases suggest, we are in the range of 90%. This is FCRI data for different valves and different sizes and different types. So this is one comparison with other conventional software, ANSYS Fluent. So where we fall if compared to other software, and we are in good range. So this is one of the case study conducted using our software. So what is the impact of outlet pressure? So one of the method to combat cavitation is to uh, use the process condition or elevate the pressure, right? So here there are the same case valve design is simulated with three different outlet pressure. So here the sigma or the cavitation index is higher. So as the sigma goes below 2, the cavitation starts. The vena contracta pressure stays above the vapor pressure line, and the moment it goes below the value 2, sigma is less than 2, the vapor pressure, the vena contracta goes below, drops below the vapor pressure, and the cavitation starts. So this phenomenon is nicely captured in our application. So finally, I'm glad to announce this wonderful exclusive offer for valve manufacturers who are attending the webinar. So our organization enterprise level yearly subscription comes at $5,000 per year. With this, you'll have unlimited valve simulations for the year. So, and no limits on the number of users, and there is no limit on the licenses and number of users. So with that, we have come to the end of the webinar. So I'll move on to the Q&A session. So one of the query I have received is, how good is the meshing? So what happens, although the meshing process is autonomous, so we make sure the mesh refinement is applied wherever it is necessary to capture the geometry, as well as to capture the flow physics and the mesh region. Okay. So wherever it is required to capture the geometry and the complex flow paths, so flow area between the holes of the trim. So there, and you can see the boundary layer, like prism layers to capture the boundary layer. So those things are captured nicely. So before formulating this strategy, we have done number of mesh independent studies. Those data are fed into the AI algorithm that applies depending on your valve type and what is the minimum area. So based on those, it selects the appropriate mesh size and things. So you can take it for sure. So the results produced are even validated. So yeah, it's the meshing is reliable, very reliable. How do you put boundary conditions for KV value? How does software calculate? Oh, okay. Good question, Saroj. So first thing is uh, the boundaries are okay. The simulations are done for 1 bar pressure drop across the valve. So that is the standard conditions. But if you have your operating conditions or something, you can provide those as well. So you can provide what is your inlet pressure boundary and what is your outlet pressure for which you want to simulate and calculate the KV. But by default in autonomous mode, we maintain 1 bar pressure. So that is the boundary condition to calculate CV and KV values. So once the pressure drop is applied to the boundary, for that pressure drop, the simulation calculates the flow rate. So use that flow rate and pressure drop and the specific gravity to calculate the KV value. Okay, so does another question is, does simulation hub provides FA solutions for machine parts? Definitely, we can connect separately and to provide insights over there. Currently, this application per se limits itself to CFD simulation, but we have this expertise, overall simulation expertise, and we can connect and understand your requirement further, and discuss further and to provide better solution for your current requirement. Okay, this question is about the approvals of bodies. Okay, so this software we have used verification and validation standards, ANSI standards. So these are the standards we follow, and this is what I was referring to, the ASME standard, verification and validation. So this software is validated using these standard procedures. It's compliant with this standard. So that's the, I hope that answers your question. Okay, interesting question again. Okay, let's say maintain 1 bar pressure. So KV value will be same for line pressure of 16 bar, inlet pressure of 16 bar, and outlet pressure of 15 bar. Yes, ideally, yes. For any pressure drop, like the pressure drop is same, and for any shift in pressure, the KV value should remain same. It will not vary. But the minimum pressure in the domain, it might change, but the incipient cavitation index and the KV value remains same. That's a constant. I guess Saroj has the same continuation question. So what happens? The delta P is same, but the inlet and outlet pressure values are changed. So in any case, for the given pressure drop, the flow rate will remain same, and the KV is also remain same. Okay, another question about whether the simulation is performed for different range of temperature of fluids we are dealing with. Oh, okay. So this is for the standard, flow loop test. So that is at 16 Celsius, like that temperature, constant temperature. You can vary the properties of the fluid right now. So we are bringing up the advanced options where you can change the viscosity and density based on the temperature. But I know we really do not model or simulate the temperature of the fluid per se. But Saurabh, you can explain what is the exact requirement of modeling the temperature. Maybe we can connect uh, after the webinar and to understand more about your requirement. Deepak has some question. Will the application be able to extract fluid domain for analysis if a machining model of the valve geometry is provided by the manufacturer? Sure, it can extract the fluid domain from those machining model as well. So if you have any sample models, we can try, and even there is a trial subscription available. So that brings me to this point also. So you can log into simulationhub.com. So you can uh, grab your trial subscription, start your trial subscription, and you can try it for yourself. And if you need any help or hands-on training to start, you can connect with the support team. So you can raise a support and request a demo. So we'll connect with you and provide the hands-on training and help you to start your simulation journey with us. Okay. So another question about liquid recovery factor. So FL we have done, we can do these simulations. So I'm planning to run another series of webinar in continuation with this. So on the FL soon you will be hearing from us about the FL simulations, like liquid pressure recovery factor. Okay, so with the interest of time, I guess we can now close the webinar. But you can, we'll put our contact email ID, so you can reach out to us for any queries or any doubts you have. So we'll be in we'll be in contact, and we'll get it resolved for you. Thanks for joining the webinar and making it very interactive session with your questions. Thanks for staying patient till the end of the webinar. Have a great day. Thanks.